Okay, so this is tutorial sheet 2, and let's get into it. So question 1 is saying average human body temperature is generally defined to be 98.6 degree Fahrenheit. Average human body temperature is generally defined to be 98.6 degree Fahrenheit. Question A, what is the temperature in degree Celsius? Question B, what is the temperature in Kelvin? So we already talked about conversions between different temperature scales, of which I specified how you can convert from degree Celsius to Kelvin and from Kelvin to Fahrenheit. So uh, what are we going to do now? We're going to say question A. Let's go to the, okay. You can just say this is our question 1. And part A is saying I should convert 98.6 degree Fahrenheit to degree Celsius. So this one is saying we convert this into degree Celsius. So how do we convert this temperature to degree Celsius? We say if we are converting from degree Fahrenheit to degree Celsius, what do? We say the temperature that we've been given in degree Fahrenheit, I'll say the temperature that we've been given in degree Fahrenheit minus 32 multiplied by 5 over 9. This is the formula that we use. So the temperature that we've been given in degree Fahrenheit is 98.6. I'll subtract 32 from this and multiply this by 5 over 9 like this. Okay, and if I plug this into my calculator, I'm getting something which looks like 66.6 multiplied by 5 over 9. And if I multiply this, I'm getting a temperature which is equal to 37.0 degrees Celsius. So that means we've converted our temperature from degree Fahrenheit into degree Celsius. And part B is saying we should convert this same temperature to Kelvin. We convert this same temperature to Kelvin. Now that we've already found this temperature in degree Celsius, remember I told you to say degree Celsius acts like the middleman between the Kelvin and the Fahrenheit, which means for you to convert your temperature from degree Fahrenheit to Kelvin, you're supposed to convert it into degree Celsius first. Even if you want to convert from Kelvin to degree Fahrenheit, you're supposed to convert to a degree Celsius first. So now that we've already converted to degree Celsius, we're just going to say temperature in Kelvin. I'll say my temperature in Kelvin will be equal to temperature in degrees Celsius plus 273.15, of which this is a constant. Now, temperature in Kelvin will be equal to 37.0 plus 273.15. Like this. Temperature in Kelvin, which is part B, will be equal to 310.15 Kelvin. So this is the final answer on part B. And when you reach that part, that means we are done with the question 1. Now we'll go to the next question, which is question 2, saying the main entrance gate to UNILUS is 8 meters long at its coldest. The gate is exposed to temperatures ranging from 22 degrees Celsius to 52 degrees Celsius. What is its change in length between these? What is its change in length between these temperatures? Assume the gate is made entirely of steel. From the table, alpha is equal to 12 times 10 to the power minus 6. So alpha is supposed to have units here. They made a bit of a mistake, but we'll get it the way it is, just like that. So let's go to this part. Say question 2 now. This is our question 2. And question 2, they've told us to say the initial length of the UNILUS gate is 80 meters. So this is the L0, what I'm going to call the L0. And this temperature is at the time when it's coldest. That they've told us to say the temperature that this gate is exposed to are ranging from 22 degrees Celsius to 52 degrees Celsius. And if these are the ranges, that means this is the coldest temperature and this is the hottest temperature. So which means at the coldest day, when this gate is 8 meters long, the temperature is supposed to be 22 degrees Celsius. Now, I find that they are telling us to say what is the change in length of the temperature, what is the change, or what is its change in length between these temperatures. So we're supposed to find the length of the gate when the temperature is 52 degrees Celsius. And they've given us to say alpha is equal to 12 times 10 to the power minus 6. And what are the units, or what units can we use for this value of alpha? We can just say it's per degree Celsius like this, because alpha, or the coefficient of expansion, should always have units. Could be per Kelvin, per degree Celsius, or in rare cases per degree Fahrenheit, because it's rarely used. So we're going to bring our formula for linear expansion. Since this is only expansion in length, we're going to say change in length is equal to alpha multiplied by initial length multiplied by the change in temperature. This is the formula. They've already given us the change in temperature. They've already given us the initial length. They've already given us the alpha. We're supposed to find the actual change in length. So we're going to say change in length will be equal to alpha, which is 12.0 times 10 to the power minus 6 per degree Celsius multiplied by 8 meters multiplied by the change in temperature, which is 52 minus 22, and this is in degrees Celsius. So our change in length will be equal to 12 times 10 to the power minus 6 per degree Celsius multiplied by 8 meters multiplied by 52 minus 22. I guess this will give us 30 degrees Celsius. So this per degree Celsius and this degree Celsius can cancel out automatically so that we just remain with the units that we are looking for. So I'm going to plug this into my calculator by saying 12.0 times 10 to the power minus 6 multiplied by 8 meters multiplied by 30. And this is giving me a change in length, which is equal to 0.00288 meters. So that is the actual change in length of the gate when the temperature is at its hottest. So this is a very small figure in meters. We're finding the change in length as 0.00288 meters. So if you want, you can convert this into millimeters, and that will just give you 2.88 millimeters. Now the question was asking to say, what is it? It's changed. They didn't ask us to say what is the final length of the temperature. So they asked us to say we should calculate the actual change in air, of which this is the value that we've found here actually. So that means that's all with question 2. That was all on question 2. Okay, now move on to question 3, which is saying concrete blocks are laid out next to each other on a highway without any space between them, so they cannot expand. The construction crew did not work on the winter day. Or the construction crew did the work on a winter day when the temperature was 9 degrees Celsius. Find the stress in the blocks on a hot summer day when the temperature is 45 degrees Celsius. The compressive Young modulus of the concrete is 20 by 10 to the power 9 newtons per square meter. Linear conductivity is alpha being equal to 12 times 10 to the power minus 6 per degree Celsius. Okay, so very simple question also. The only thing you're supposed to really take note of is that we are integrating stress. We were talking about stress in topic 1, and we are integrating it to relating it to thermal expansion. So how does stress actually relate to thermal expansion? We're going to use this formula to say stress is equal to the Young's modulus multiplied by the coefficient of compressive modulus in concrete, or alpha. So this is the coefficient of or the compressive Young modulus in the concrete is this guy gamma there. Then we have alpha representing linear conductivity, and we're going to multiply this by the change in temperature, and that is the formula that is going to give us the stress that we are looking. So they've already given us the value of the Young modulus or compressive Young modulus in concrete to say it is equal to 20 times 10 to the power 9 newtons per square meter. Then they've given us the alpha linear conductivity to say this is 12 times 10 to the power minus 6 per degree Celsius. And what else? We have already been given the change in temperature, and this is equal to what? It's equal to the final temperature minus the initial temperature. So they told us to say the final temperature is 45 degrees Celsius, whilst the temperature on the day of construction was 9 degrees Celsius. So that means our change in temperature is going to be equal to 36 degrees Celsius. And I'm going to plug this into my equation here to say stress, compressive stress will be equal to what? Will be equal to 20 times 10 power 9 newtons per square meter multiplied by 12 times 10 to the power minus 6 per degree Celsius multiplied by 36 degrees Celsius. So this 36 degrees Celsius will cancel out with this 36, or I mean with that per degree Celsius. 1 is a denominator, the other one is a numerator. And what are we remaining with? We're remaining with 20 times 10 to the power 9 newtons per square meter multiplied by 12 times 10 to the power minus 6 multiplied by 36. So our stress will be equal to what? Okay, so let me just punch it all together in my calculator. Okay, so I'm getting an answer which is equal to 8640. 8640 times 10 to the power 3 newtons per square meter, of which I can simplify this further by moving the point maybe up to there. Yes, I think up to that point. That means we're going to have 8.64 times 10 to the power 6 times 10 to the power 6. I've gone 3 more steps to the left. That means this to the power 3 is going to change to power 6, and this is in newtons per square meter. And we have calculated the compressive or the compressive stress, the stress in the blocks after that particular change in temperature. So that is the value of stress, which is equal to 8.64 times 10 to the power 6 newtons per square meter. And that is all on question 6. That is everything we can, or we're supposed to find on question 6. Let's go to the next question, which is question 4. Did I just say question 6? I meant to say question 3. Question 4 is saying a 50.0 gram sample of copper is at 25.0 degrees Celsius. If 1,200 joules of energy is added to it by heat, what is the final temperature of the copper? A 50.0 gram sample of copper is at 25.0 degrees Celsius. If 1,200 joules of energy is added to it by heat, what is the final temperature of the copper? So this is a very interesting question and also a very simple question at the same time, because we're relating this question to having or finding the specific heat capacity of that particular substance we've been given. So they've given us the amount of heat that is added, which we'll call Q, to say this is 400 joules of energy. So that's the amount of energy that has been added. And we've also been given the mass of the copper, say it is 50 grams. You can actually convert this into kilograms by dividing it by 1,000, and we're going to get mass, which will be equal to 0.050 kilograms, like this. Then we have the C of copper, which is the specific capacity. And if I look at this question, they didn't really give us the specific heat capacity of water, but they said in at the top there to say for physical constants that are not given, you should refer to tables in your lecture notes. So we're going to get the specific heat capacity of your copper directly from your lecture notes, of which this is approximately 385 joules per kg degree Celsius. That is the specific heat capacity of water. And then we also have the change in T. So they've asked us to say we should calculate the final temperature, which means we want to find the change in T. They've given us the initial temperature to say it's 25 degrees Celsius. So if this is the T initial or T0, how are we going to find the change in temperature? So let's bring the formula for calculating the amount of energy supplied using the specific heat capacity. We're going to say Q is equal to M, which is the mass, multiplied by C, multiplied by change in temperature, which in this case, the C is for copper. The M is also for copper. So Q, which is 1,200 joules, this will be equal to the mass of the copper, which is 0.050 kilograms, multiplied by the C of copper, which is 385 joules per kg degrees Celsius, like that, multiplied by the change in temperature, like that. Okay, so this kg can cancel out with that kg. That means we've forgotten about our kg. So what are we going to do? We are looking for change in T, or let's just collectively find change in T without complicating anything. Because if I say T final minus T initial in this or at the end where there is T here, we're going to be supposed to distribute this that is in the brackets to everything that is outside here, which will be somehow a bit complicated. So let's just make change in T the subject of the formula, of which I'm going to do that by dividing both sides of our equation by 0.50 kilograms multiplied by 385 joules per degree Celsius. So I said kg and kg has cancelled out, so which means this kg has to disappear. Okay, so from there, what are we going to do? We're going to notice that on this side, everything is going to cancel out. I'm going to wrap instead of cancelling out. Then I'm going to remain with change in T will be equal to 1200 joules divided by 0.50 times 385 joules per degree Celsius. So the joules and the joules can also cancel out. That means what am I remaining with? I'm remaining with a change in T being equal to, I can multiply the numerator there, which this is giving me 1200 divided by 19.25, like this. This is per degree Celsius. So 19 into 12 or 19.25 into 1200, I'm getting a final temp or a change in temperature, which is equal to 62.34 degrees Celsius. So this is the change in temperature. And if this is the change in temperature, they gave us to say the initial temperature was 25 degrees Celsius. So for us to find the change in temperature, we're going to notice the change in T will be equal to T final minus T initial. So we're looking for T final, which means T initial is going to go on the other side. So I'm going to say the change in temperature, which is 62.34. Then I'll get this guy and take it on the other side. It will become a positive. So plus initial temperature, which is 25. This is going to give me T final. Then 62.34 plus 25 degrees Celsius. This is giving me the final temperature T final of 87.34 degrees Celsius. So that is the final temperature in this case. And if we reach that part, that means we are done with this question 4. Okay, so let's move on to question 5. Okay, we're now going to question 5, and question 5 is saying a 0.500 kg aluminium pan on a stove and 0.250 liters of water in it are heated from 20 degrees Celsius to 80 degrees Celsius. Question A, how much heat is required? Question B, question B is saying what percentage of the heat is used to raise the temperature of B, the pan, and C, the water? So this is a very interesting question. They've told us to say if a 0.5 kg aluminium pan on a stove and 2 point and 0.25 liters of water in it are heated from 20 degrees Celsius to 80 degrees Celsius. So this is the change in temperature. Then they're given us to say A, how much heat is required, which means how much heat is required to heat the temperature of this guy is from 20 degrees Celsius to 80 degrees Celsius. Then what percentage of the heat is used to raise it? B, the pan, C, the water. So that's a very, very interesting question. And here is how we're going to handle it. Let's get on the data. so this is question 5. And question 5, we've been given to say we have a pan with a mass of 0.5 kilograms. Then you also have water, of which this water has a volume of 0.25 liters. I guess this is what we've been given. And these guys are heated from 20 degrees Celsius to 80 degrees Celsius. So how much heat? Question A is saying how much heat is required to give us this change in temperature of from 20 degrees Celsius to 80 degrees Celsius. So what are we going to do? So we're going to find the amount of heat that is required to change the temperature of water or of the aluminum pan from 20 degrees Celsius to 80 degrees Celsius. And when we do that, we can also do what? Calculate the heat that is required to raise the temperature of water from 20 degrees Celsius to 80 degrees Celsius. So let's do just that. Let's do just that. First, we have to provide the C, which is the specific capacity of aluminium, since the pan is made up of aluminium. We'll say of aluminium. Then we also are supposed to have the specific capacity of water. So the specific capacity of aluminium is 900 joules per kg degree Celsius. Whilst the one for water is 4186 joules per kg degree Celsius, or which sometimes this one is just used as 4200 joules per kg degrees Celsius. So first, before we start solving, we have to make some assumptions because they've told us to say water is on the pan. So what assumptions must we make is that during this process of heating this water, there should be no water that should evaporate. That means we should assume that there's no exchange of energy between the system that we've been given and the surrounding that we have. So what are we going to do? Let's now use the formula. The formulas that I told you to say the Q, the amount of heat used to raise the temperature of the pan will be equal to mass of the pan multiplied by C of aluminium multiplied by the change in temperature. Because here the Q of water will also be equal to what? Will also be equal to the mass of the water multiplied by the C of the water multiplied by the delta T, like that. So the amount of heat used to raise the temperature of aluminium will be equal to 0.5 multiplied by 900 multiplied by the change in temperature, which is 80 minus 20 degrees Celsius. I'm going to say the Q required to heat aluminium will be equal to half multiplied by 900. That will give us somewhere 450. And if I multiply that by 60, which is the temperature difference in the brackets, I'm getting an answer which is equal to 27,000 joules. So this is the amount of energy that is required to raise the temperature of the pan from 20 degrees Celsius to 80 degrees Celsius. Let's go to the water. This will be equal to the mass of the water, of which do we know the mass of the water? Have we been given the mass of the water? Okay, we haven't been given the mass of water. So what are we going to do? We're supposed to find the mass of the water first. Before you start doing anything, you're supposed to find the mass of the water, but we have a 4186 here multiplied by 60 also as usual. So how are we going to calculate the mass of the water? Remember, we already know the density of water. We know the density of water, and what else do we know? We also know the volume of the water that we've been given. So what are we going to do in order for us to find the heat required to raise the temperature of our water? We can use that same formula to say density is equal to mass of volume. You're looking for mass, we already know the volume, we already know the density of water. And if you plug everything into this formula, you're still going to get the mass of water to be equal to 0.25 kilograms. Like that. So I'm going to put here 0.25 and I'll patch this into my calculator and I'm finding the Q of water to be equal to what? The amount of energy used to raise the temperature of water to be equal to 62,790 joules. 62,790 joules. So this is the amount of energy that is required to raise your temperature of the water. Now they asked to say, in part B, they said how much heat is required. So in order for us to find the summation of the heat required, we're just going to say the Q total will be equal to Q required to heat aluminium plus the Q required to heat water. This will be equal to what? This will be equal to 27,000 plus 62,790. 62,790. Remember the units we have joules. And if I add these together, I'm getting 89,000. 89,790, like this, of which this is in joules. If you want, you can just say this is the same as 89.79 kilojoules. 89.79 kilojoules, just like that. So that is the amount of energy that is required to heat both the water and the pan from 20 degrees Celsius to 80 degrees Celsius. Now they've told us to find the percentages to say how much or what is the percentage of the heat that is required to heat the aluminium and the one that is required to heat the water. So that is very simple. We're just going to say percentage of heat required to heat the pan will be equal to what? Will be equal to the Q that is used to heat the pan over Q total multiplied by 100. This is going to be equal to what? This is going to be equal to 27 kilojoules over 89.79 kilojoules multiplied by 100%. So that means the percentage of heat that is required to heat the pan is equal to what? Is equal to 30.07%. Like this. Also do the same to the percentage of heat required to heat the water. And this will be equal to Q over Q total multiplied by 100%, like that. This will be equal to what? This will be equal to 62.79 kilojoules divided by 87 or 89, sorry, 0.79 kilojoules. This multiplied by 100%. And we're going to get the final percentage of the heat that is required to heat the water as 69.93%, like this. So that is the percentages that are required to heat the pan and the water respectively. And when we reach that point, that means we are done with question 5.